Hi, my name is Ganardi, and this is joint work with Figelius, Markus Lohrey, and Georg Zetzsche. And the topic of this talk is algorithmic group theory, and in particular we look at the so-called knapsack problem. So what is the knapsack problem? Suppose we have a group G with a finite set of generators sigma, which means that we can represent elements from the group as words over the finite set of generators sigma. Then the knapsack problem for G asks, given group elements G1 to Gn and H as words over sigma, does this equation have a solution? Meaning, are the natural numbers x1 to xn such that G1 to the x1, G to the x2, and so on is equal to H? And this problem was defined in 2015 by Myashnikov, Nikolaev, and Ushakov, and has since then been studied for various groups. For example, if we look at the group of integers, then the knapsack problem is precisely the classical problem of solving linear Diophantine equations. And here we have to be a bit careful with the representation of the numbers. Namely, if the coefficients ai and b are given in binary, then the problem is NP-complete. However, if we give the numbers in unary, then the problem actually is solvable in polynomial time. In fact, it's complete for the circuit complexity class TC0. And since, as I described before, we represent the elements as words over the generators, this corresponds to a unary encoding. So we would say that knapsack for Z is in TC0. But of course, the knapsack problem becomes more interesting for non-abelian groups. And we try to study the following questions. For which groups is knapsack decidable? And what is the complexity? Now let me mention a few decidability results that we know for knapsack. So we know that knapsack is decidable for hyperbolic groups, co-context-free groups, and right-angled arcing groups. And don't worry, the precise definitions of these groups are not so important. And furthermore, there are a couple of closure properties for knapsack. For example, finite extensions, which means if we have a group G, and it has a finite index subgroup H, and knapsack is decidable for the subgroup H, then we also know that it's decidable for the larger group G. And similar results hold for other constructions from group theory, like H and N extensions over finite associated subgroups, or amalgamated free products over finite subgroups. Now let me introduce a second related problem, called the power word problem for a group G. Here we are given group elements G1 to Gn and binary encoded numbers K1 to Kn. And the question is whether G1 to the K1 up to Gn to the Kn is equal to 1. This is a variant of the classical word problem for a group, where you are given a single word over the generators and you ask whether this element is the identity. Here the word power refers to the exponentially large powers K1 up to Kn. And this representation can be compared to a binary encoding for integers. Our motivation to study the power word problem is the following. We can prove that knapsack is in NP in two steps. First, show that if there is a solution, then there is always an exponentially bounded one. And second, prove that the power word problem is in polynomial time. But of course, the power word problem is also of independent interest. Since we are dealing with exponentially long products, a priori there could be an exponential gap between the complexity of the word problem and the power word problem. But interestingly, Markus Lohrey and Armin Weiss showed that for many groups, the two problems actually have the same complexity. For example, for free groups or nilpotent groups. Let me also mention this old result of G, where the power word problem was studied implicitly. And he showed that one can verify in polynomial time identities of the form alpha1 to the k1, alpha2 to the k2, and so on, where the alpha i's are elements from an algebraic number field. Now, for many groups, the solution sets of knapsack equations are actually semilinear. Let me briefly recall the definition of semilinear sets. A subset L of n to the d is linear if there is a base vector u and finitely many period vectors vi such that L is equal to the base vector plus the span of the period vectors Vi. And a set is semilinear if it is a finite union of linear sets. So semilinear sets are some kind of generalization of ultimately periodic sets into higher dimensions. Equivalently, the semilinear sets are precisely the relations definable in Pressburger arithmetic, which is first-order logic over the natural numbers with addition. In particular, the semilinear sets are closed under Boolean operations, and therefore they are a very important tool in automata theory and logic. Now let us call a group knapsack semilinear if for every knapsack equation the set of all its solutions is effectively semilinear, which means that the solution set is a semilinear set, and one can actually compute a semilinear representation from the equation. Clearly, if a group is knapsack semilinear, then knapsack is decidable, because emptiness is decidable for semilinear sets. But the converse does not hold, as we will see on the next slide. As a simple example, the group of integers is certainly knapsack semilinear, since given a Diophantine equation of this form, we can compute a semilinear representation of the set of non-negative solutions. The reason that we study knapsack semilinear groups is that they have better properties than groups with decidable knapsack problem. For example, let's look at the direct product of groups. If we are given a knapsack equation over the direct product of two groups G and H, then the solution set is the intersection of two solution sets over G and over H. And so if we know that these two sets are semilinear, then their intersection must also be semilinear by the properties of semilinear sets. Hence, knapsack semilinearity is preserved under direct products. And this does not hold for decidability of knapsack. For example, we know that knapsack is decidable for the so-called discrete Heisenberg group, which is the group of unitriangular matrices over the integers in dimension 3. However, it becomes undecidable if we take the direct product of m copies of the Heisenberg group, where m is some fixed number. In particular, decidability of knapsack is not preserved under taking direct products. Another construction which preserves knapsack semilinearity is the wreath product. The wreath product is a fundamental construction in group theory and semi-group theory. It can be used, for example, to study free solvable groups, since free solvable groups can be embedded into iterated wreath products of free abelian groups. This is the famous Magnus embedding. So let me first give you the formal definition, which may seem very technical at the first glance, and then a more intuitive picture on the next slide. So let G and H be groups. Then we denote by G to the H the set of all functions from H to G with finite support. That means only finitely many elements are not mapped to 1. The wreath product G wreath H is the set of all pairs f, h, where f is such a function with finite support and h is from H. And the multiplication of two pairs is given as follows. In the right component, we simply multiply the elements h1 and h2. But in the left component, we get this function f, which is defined here on the right-hand side. As an example, consider the wreath product of z and z squared. This group acts on the set of all finite labelings of the infinite grid together with a single cursor in the grid. The generators of the wreath product can then be viewed as basic operations on these configurations. First, we have the generators of z squared, which are the unit vectors, which can move the cursor in the grid. Second, we have the generator +1 of z, which can add to the value in the current cell in the grid. With this intuition of the wreath product in mind, let us turn back to the knapsack problem and the power word problem. It is convenient to assume a certain normalized form. Say that a power word over a wreath product G wreath H is normalized if each of the elements ui is a product of some gi in G and some hi in H. So this means U1 puts G1 in the current cell and then moves the cursor by H1. And this is repeated K1 many times. Then U2 puts G2 into the current cell, moves the cursor by H2, and so on. For the cases that we will consider, we can always assume normalized power words. And for the knapsack problem, we can also assume a similar normal form. So again, the question is, for which wreath products is knapsack decidable? In a previous paper, we proved that the situation is just as for direct products. First, the negative result: there are two groups for which knapsack is decidable, but it becomes undecidable for the wreath product. But if two groups are knapsack semilinear, then their wreath product is also knapsack semilinear. And as a corollary, we obtain that knapsack is decidable for free solvable groups. As I mentioned before, they can be embedded into iterated wreath products of z to the r, where this parameter r is determined by the rank and the depth is determined by the so-called derived length of the free solvable group. And since the abelian groups z to the r are easily seen to be knapsack semilinear, also this iterated wreath product is knapsack semilinear, and hence also every free solvable group, since we can embed it into this wreath product. However, this does not give us good complexity results, since the proof here involves complementations of semilinear sets. In the same paper, we also show two complexity results, namely that knapsack is in NP if the left group is abelian and the right group is Z, and also knapsack is always at least NP hard as soon as G is non-trivial. In this paper, we present new complexity results for the knapsack and the power word problem. We show that knapsack is in NP for G wreath Z if G is a finite nilpotent group. Previously, this was only known for abelian groups G. And knapsack is also in NP for iterated wreath products of free abelian groups, and hence also for free solvable groups by the Magnus embedding. These results for knapsack are obtained from the following results on the power word problem, namely the power word problem is in TC0 for wreath products of nilpotent groups with Z and for iterated wreath products of free abelian groups. Of course, the question arises, what happens if G is not nilpotent? And here the situation is not very clear. We have the abelian groups, which are subsumed by the nilpotent groups, which are in turn subsumed by the solvable groups. And we can only prove lower bounds for non-solvable groups with some extra conditions, and these groups are called uniformly, strongly, efficiently non-solvable groups, or short, uniformly sense. Namely, if G is uniformly sense, then the power word problem for G wreath Z is co-NP hard. And this stands in contrast to the TC0 bound if G was nilpotent. And if G is uniformly sense, then the knapsack problem for G wreath Z is sigma 2p hard, in contrast to the NP bound for nilpotent G. These uniformly sense groups were defined in a recent paper, which will appear at CCC this year. And roughly speaking, these are groups which can simulate the proof of Barrington that the word problem for finite non-solvable groups is NC1 hard. So this leaves a gap between the solvable and the nilpotent groups for both the power word problem and the knapsack problem. For the rest of the talk, I want to give you some ideas of the proofs. Let's start with the statement that the power word problem for wreath products of nilpotent groups and Z is in TC0. Consider an instance of the power word problem. Each of the elements Ui have either non-zero shift in Z, like these two elements, or the shift is zero, like this element U3, depicted by a loop. We can see that the power word produces a superposition of periodic labelings of Z. Now we can decompose this picture into polynomially many pieces. First, we have points with loops. Such columns are instances of the power word problem for the group G. And in fact, we know that the power word problem for finitely generated nilpotent groups is in TC0. The rest consists of exponentially long superpositions of periodic labelings. We call the remaining problem the periodic words problem over G. Let us make this more formal. For a group G, let G to the omega be the group of all infinite sequences over G. This forms a group with pointwise multiplication. A sequence has period D if f of t plus d equals f of t for all t. Of course, we can represent a sequence with period d by specifying its first d elements. Now the problem that remains to solve is the periodic words problem over G, which is, given periodic sequences f1 to fn and some bound t in binary, does the pointwise product, called f, evaluate to 1 in the first t entries? The difficulty of the problem is that if the input sequences have periods d1 to dn, then the product sequence is also periodic, but the period can be exponentially large. In the worst case, it can be the product of the periods di. So naively, we would have to compute exponentially many entries of f. Still, our claim is that periodic words over nilpotent groups is in TC0. Let us first assume that G is an abelian group. Then f should rather be called the sum and not the product of the input sequences fi. Now the periodic words problem can be solved using the theory of linear recurrent sequences. Namely, it is known that f satisfies a recurrence of order d, where d is the sum of the periods di. This means that every entry in f is a linear combination of the previous d entries, where the coefficients ak are some fixed integers. The point is that we move from the space of periodic sequences to the space of linear recurrent sequences. And we use this well-known fact that if a sequence f satisfies a recurrence of order d and g satisfies a recurrence of order e, then their sum f plus g satisfies a recurrence of order d plus e. In particular, this equation implies that the sum f is identically zero if and only if it is zero on the first d entries. So we only need to check polynomially many values, which can be done in TC0. Now for nilpotent groups, let me only give you the definition of nilpotent groups, which I haven't defined so far, and the generalization of this idea without a proof. Nilpotent groups are defined using the notion of commutators. The commutator of G and H is G inverse times H inverse times G times H. And it's not so hard to see that a group is abelian if and only if all commutators are trivial. Now, a group is defined to be nilpotent if all nested commutators for a fixed nesting depth are trivial. Now, a natural generalization for the notion of linear recurrent sequences is the following. An infinite sequence f over G satisfies a recurrence of order d if every entry in f can be written as a fixed product or a fixed word over the previous d entries and its inverses. For example, f of t plus 3 is f of t squared times f of t plus 1 inverse, and so on and so forth. For all t, there's some fixed word which describes f of t. And then we could prove the following lemma. Let G be a nilpotent group, then there exists a polynomial p of m such that any product of sequences with period at most m satisfies a recurrence of order p of m. In particular, the product is identically 1 if and only if it is 1 on the first p of m entries. So it suffices to check them. If they are trivial, then we know that the entire sequence is trivial. Let us now look at knapsack for G wreath Z. Suppose we are given a knapsack equation of this form. Then we distinguish variables xi where the ui have non-zero shift in z or have zero shift in z. In the previous paper, we already observed that if there is a solution, then there's always a solution where the shifting variables are bounded exponentially. And so we can simply guess their values in NP and verify the periodic intervals using the power word problem. The rest constitutes a system of polynomially many knapsack equations over the non-shifting variables. And well, this can be undecidable for arbitrary nilpotent groups, and this is why we add the condition that G must be finite. And for any finite group G, systems of knapsack equations is in NP. The most technical result from this paper is the one on the iterated wreath products of free abelian groups, namely that the power word problem is in TC0 and knapsack is in NP. Let me comment on this theorem a bit. So we already know that these groups are knapsack semilinear, since the abelian groups z to the r are knapsack semilinear, and knapsack semilinear groups are closed under taking wreath products. We strengthen this statement by showing that the solution sets of knapsack equations over these groups in fact have small magnitude. So here's the definition. If S is a semilinear set, then the magnitude of a semilinear representation R for S is the maximal number which occurs in R. And the magnitude of S is the smallest magnitude of all semilinear representations for S. Now we actually show a stronger statement. Let G be an abelian group and H be an orderable group. The precise definition of orderable is not so important here. If knapsack solution sets over H have exponential magnitude, then the same holds for G wreath H. And by exponential magnitude I mean that if the knapsack equation has length n, then its solution set must have magnitude exponential in n. And in particular, this means that if there is a solution, then there is always an exponentially bounded one. So we can simply guess it and verify it using the power word problem in TC0. So let me conclude. Instead of reiterating all results again, let me mention some results which are related to our work on the power word problem. We have seen that the power word problem for G wreath Z is in TC0 if G is nilpotent, and co-NP hard if G is uniformly sense, for example if G is finite non-solvable. This leaves a gap for solvable groups which are not nilpotent. The same gap is also known for other problems called equation satisfiability and equation identity. Equation satisfiability was first studied by Goldman and Russell. Let's look at the dual problem equation identity. The input is an equation W1 to Wn equals 1, where the Wi are either variables, inverted variables, or group elements. And the question is whether every variable assignment makes the equation true. So here we assign group elements to the variables and not natural numbers. Goldman and Russell showed that the problem is in polynomial time if G is nilpotent, and later it was shown that the problem is co-NP complete for non-solvable finite groups. In a paper which also appears in this ICALP, Armin Weiss constructed finite solvable groups for which equation identity is not in polynomial time under the exponential time hypothesis. Now, there is a simple reduction from equation identity over a group G to the power word problem over G wreath Z. So this means for these solvable groups constructed by Armin Weiss, it is unlikely that the power word problem is in polynomial time. But of course, one could look at restricted classes of solvable groups. Thank you for listening, and I would be happy to take questions during the online sessions.